Okay, welcome to lecture, and we'll get started in just a minute or so. We're going to pick up where we were left off. I think it's chapter 8 in gases. So we'll just start in a minute or so. And like usual, again, if you have questions anytime through the lecture, feel free to ask them in the chat box and we'll get to your question. All right. So again, we started talking about gases last time, and obviously there's a lot of gas laws that you do need to know. So we got through Boyle's law, which is our P1 V1 equals P2 V2. That's at constant temperature. And Boyle's law basically saw that as the pressure goes up, the volume goes down, and vice versa. If the pressure goes down, the volume will go up, and it's sort of an inverse relationship. One goes up, one goes down. We also talked about Charles' law, which is V1 over T1 equals V2 over T2. And that is at constant pressure. And the way it's able to maintain constant pressure is the volume will adjust. And sort of the trend that we see with that is as the volume goes up, so does the temperature. And again, as we increase the temperature, everybody has more energy. So to keep the pressure constant, the volume needs to adjust in that case, and vice versa. If we lower the temperature, our gas molecules will be flying around slower, which would lead to less collisions and the pressure would go down. But to fix that so the pressure doesn't vary, the volume will go down with it. So Charles' law, which is the V1 over T1 equals V2 over T2, as one goes up, so does the other. So temperature up and volume goes up with it, and temperature goes down, volume will go down with it as well. Now, that temperature, pretty much like every gas law, does need to be in Kelvin. So one thing that sort of came out of experiments done by Kelvin actually was that you need to basically convert the temperature from Celsius to Kelvin by adding 273 to do that. Even if they give you the temperature in Celsius and want you to give the answer in Celsius, you still need to convert it to Kelvin when you go into the gas law and then convert it out from Kelvin. We also saw Guy-Lussac's law, which is a similar type of law, but involves pressure and temperature where the volume remains constant. And in that case, the volume won't be able to adjust to manage any type of pressure situation. So basically, the volume is fixed or rigid. And in that situation, which is P1 over T1 equals P2 over T2, as the pressure goes up, so does the temperature. And again, in that situation, because the volume is not moving, when we increase the temperature, we have an increase in the rates of collision. The rates of collisions will lead to a higher pressure that we see, and vice versa. If we lower the temperature, then we will have less collisions. Less collisions will result in less pressure. And again, because the volume is not moving, like in Charles' law, it has no way to maintain the pressure, so the pressure goes up as the temperature goes up, and the pressure goes down as the temperature goes down. Also, again, the temperature there does need to be in Kelvin. Any questions on that before we sort of begin? So I think we left off with this example. So why don't you take a couple minutes here and work out this example and see what you get, and then we'll talk about it. So carbon monoxide has 3.2 liters at 125 degrees Celsius. What's the temperature if the volume is 1.54 liters? So take a minute or two, and then we will talk about the answer. See how you do. Okay, so we have a few gas laws to choose from. And as we talked about before, sometimes it's good to sort of pull out the information. So we obviously have a volume that is 3.2 liters. And then we have a temperature that is 125 degrees Celsius. We want to know what the temperature is if the volume becomes 1.54 liters. So again, you could kind of look at this if you just kind of pull out the information. If you're not really sure which one you should use, then obviously here Charles' law would be probably the best choice. V1 T1 equals V2 T2, especially this is at constant pressure, which is what Charles' law is all about. Now, in terms of our ones and twos, usually we just take the first numbers in the problem. I'm going to go in order. It doesn't really matter as long as you keep the numbers together. So in this particular case here, our volumes are both liters, but we do have to again convert our Celsius into Kelvin. So we want to add 273 to that. That's going to give us 398 Kelvin. So you can see we have V1, we have T1, we have V2. So we are looking for T2 here. When you move across the equal sign, everybody ends up in the opposite location. So if you rearrange this, you will end with something like so. Again, multiplying the T2 to the other side, multiplying the T1 to the other side, and dividing by the V1. We do want to make sure we get everybody in the right spot there. So V2 is 1.54 liters. T1 is 398 Kelvin. And divided by our V1, which is 3.2 liters. Liters are going to cancel. That's going to leave us Kelvin as our answer, which is good because that is a temperature. And if we do all that good stuff, it looks like 192 Kelvin would be the answer here. It didn't really specify units. If we actually wanted Celsius, we could subtract 273 from it, and we would actually get minus 81.5. Would be our degrees Celsius answer. But again, in this case, it didn't specifically ask for any particular units there. Any questions on that calculation, where the numbers came from, or anything like that? Again, you want to make sure that you do know how to obviously rearrange these equations. You do need to be able to solve for anything. So sort of the simplest way to rearrange, if rearrange is not your thing, you know, you can think of both sides of a fraction. Everybody ends up in opposite locations. If you go across the equal sign, you just basically put them in sort of the opposite locations. Any questions on that one? Okay, so why don't you try the next one that we have, I think. So we have 452 milliliters of a gas is used for a light bulb. It goes from 22 degrees Celsius to 187. What is the final volume in this case? So take a minute or two, see what you come up with. Okay, so let's see how we're doing. I see an answer. Let's see how we did then. Again, here, if you're not sure, you can just pull out the information. We got a volume that's 452 milliliters. We got a temperature that's 22 degrees Celsius. We have another temperature that's 187 degrees Celsius. And again, in this case, we are looking for a volume. So much like the first one there, you could kind of almost see Charles' law there. And in this particular case, we're going to be solving for V2. If we rearrange it, V2 would equal, again, we're just going to move our T2 to the opposite location, which would move it to the top. And we would end up with T1. Just like before, we do have to do some addition here and convert our temperatures into Kelvin. And in this particular case, we will end up with 295 Kelvin. We will add 273 to this one, and we'll end up with 460 Kelvin. We can leave our volume in milliliters. All it means is our answer will be in milliliters. So putting our numbers in, our T2 at 460 Kelvin divided by our 295 Kelvin. Again, the Kelvin's going to cancel. We will end up with milliliters as our answer. And I believe you do got the correct answer there, so that's good. We will end up with 705, very badly written, try it again, 705 milliliters in this particular case. Any questions on that calculation? Now, again, if you remember, there is, sort of a way to make sure that you didn't maybe mess up on putting numbers in the wrong spot. It's very common. People will put like T1 where T2 should go and vice versa. If we remember when we talked about Charles' law, the relationship that we see is as the volume goes up, so does the temperature. And as the volume goes down, so does the temperature. So when we look what happened, say from here to there, from our first temperature to our second, temperature went up. So we would expect the volume to go up. So it went from 452 to 705. So it did obviously do what we would expect it to do. And our number does make sense. We also will see that here, which was also Charles' law. In this particular case, our volume went down, which means we would expect the temperature to go down as well. And again, we saw that here. It went from 398 to 192. So again, sometimes it's good to understand sort of the relationships of these gas laws, because mathematically speaking, sometimes, we invert numbers or sort of mess up numbers, so we can make sure that our number does make sense. Any questions on that there? All right, one more example. Let's see how you do there. So we're looking for the final pressure here in atmospheres. So again, take a minute or two to see what you come up with. Let's see how we all did. Okay, so here again, excuse me, following the same approach, we kind of pull out the information. We have a pressure that is 1.2 atmospheres. We have a temperature that's 18 degrees Celsius. We have another temperature that is 85 degrees Celsius, and we have a pressure, which is what we're looking for. Again, you should hopefully kind of recognize this as Guy Lutz's law, which is P1 over T1 equals P2 over T2. This is at constant volume, this particular relationship. Kind of works the same way in terms of the pressure. It doesn't really matter the units as long as they are the same units. So in this case, we would be solving for P2. So if we rearrange that again, P2 would equal our P1 times our T2 divided by our T1. Again, basically moving this guy to the opposite location when we do that. Much like most gas laws, right? We need to start with our temperatures and make sure they're in Kelvin. So adding our 273 to our first one gives us 291 Kelvin, and adding our 273 to our second temperature there does give us 358 Kelvin. And again, we just want to make sure that we put everybody in the right spot. Our T2, which is 358, divided by our 291 Kelvin. Here, the Kelvin is going to cancel each other out. That's going to leave us in atmospheres, which is good because that's actually what we're looking for. It's also obviously a unit of pressure, and that does give us 1.48 atmospheres. In this particular case. And looks like you did good in the box as well, so that is good. Any questions on that calculation? Again, we could think about sort of this gas law and the relationship that we talked about, because this is at constant volume. As the pressure goes up, so does the temperature. And as the pressure goes down, so does the temperature. And in this case here, we have an increase in the temperature, which means we should see an increase in the pressure. And again, it went from 1.2 to 1.48. So the pressure did increase. So again, this is just a way you could kind of check your calculation to make sure you didn't accidentally invert any numbers, put some numbers in the wrong spot. Any questions on that there, those examples? Okay. So continuing on, we're going to talk about another gas law, which is our good friend Avogadro. So Avogadro, he had a number. He also had a gas law. And his gas law is what we see here. This is V1 over N1 equals V2 over N2. And this occurs at constant temperature and pressure, like the guy's yelling there to the right. So under constant temperature and pressure conditions, V is volume, N is moles. So N is the moles of the gas. So N is moles. And V1 over N1 equals V2 over N2. And you could use Avogadro's law like a normal gas law. You can plug and chug into it and, solve for a volume if you know the moles and another volume. You solve for a mole if you know two volumes and a mole. So you could plug in, sort of chug into there. Another sort of aspect of Avogadro's law is when you're doing something, for example, like gas stoichiometry or stoichiometry that involves gases. We can use sort of Avogadro's law, especially when it's at constant temperature and pressure, to really come up with a relationship much like what we do when we do normal stoichiometry. So when we do normal stoichiometry, if we have an equation that has all gases, we would look at the coefficients and we would say, for example, that's 3 moles of H2 react with 1 mole of N2, gives us 2 moles of NH3. So really the volume is proportional to the number of moles. So we actually can come up with a volume relationship. 3 volumes of H2 equals 1 volume of N2, and that gives you 2 volumes of NH3. So from this particular equation, we could do almost like a stoichiometry relationship. We could say a lot of times 3 liters of H2 would be equal to 1 liter of N2. We could say 3 liters of H2 that we put in there would get us 2 liters of NH3. We could also do 1 liter of N2 would produce us 2 liters of NH3. And just like in stoichiometry, we could do, instead of a mole to mole relationship, we could do a volume to volume relationship where we could write conversion factors like 3 liters of H2 over 1 liter of N2 are 1 liter of N2 over 3 liters of H2. And the benefit of this is sometimes if you're doing some type of stoichiometry problem that involves gases at constant temperature and pressure, it will allow you to really figure out the volume of each of the gases that are either produced or you started with, just doing a basic stoichiometry problem rather than having to use some type of gas law to sort of figure that out. So sort of a practical application of Avogadro's law, which again, you can use Avogadro's law like any of the other gas laws. You could just plug numbers in and obviously solve for something. But in a constant temperature and pressure situation, you could use this relationship to sort of do a stoichiometry problem. So for example, if we look at this problem here and ammonia burns in oxygen to form nitric oxide and water vapor, how many volumes of NO are obtained from 1 volume of ammonia at the same temperature and pressure? Now, you could do really a stoichiometry problem here, as we'll see later on, where you use sort of the ideal gas law and some other gas laws to sort of solve this. But because this is all gases and we have the important part here, constant temperature and pressure, we could look at this and basically do the problem here where we want to know basically how many NOs we could produce if we started with 1 volume of ammonia. So from the actual relationship, we could say that there are 4 liters of NH3 gives us 4 liters of NO, which again, we could do 4 liters of NH3 over 4 liters of NO, are just like we do a mole to mole relationship, 4 liters of NO over 4 liters of NH3. Obviously, in this case, that is also the same as a 1 liter of NH3 gives us 1 liter of NO, which obviously we could write the same type of conversion factors. So if we started with 1 liter of ammonia, we can use the volume to volume relationship that we could get from the equation. And we see again, you use the 4 liters of NH3 gives us 4 liters of NO, and we would expect to produce obviously 1 liter of NO in this case. So sort of a practical application, almost like a shortcut in certain cases, especially when you're doing a stoichiometry problem with gases that involve constant temperature and pressure. You could do a volume to volume relationship because really is sort of consistent with a mole to mole relationship that we see. And again, that's really based off of Avogadro's law. Any questions on that? So later on in the chapter, we'll definitely talk a little bit more about gas stoichiometry, and you should keep this in mind, especially if you come across a sort of a problem that involves constant temperature and pressure, and you have to do sort of a stoichiometry problem. It can make it a lot easier of a problem to sort of finish and do. Any questions on that? All right. So looking at these are again just the relationships of these different gas laws that we talked about. We had our Boyle's law, which is again our P1 V1 equals P2 V2. Smaller volume, higher pressure, higher volume, lower pressure. We also saw with Charles' law, again, as the volume increases, so does the temperature to keep that constant pressure. And as the volume decreases, the temperature will go down as well. And we see the same thing with our pressure and temperature, higher temperature, higher pressure when the volume doesn't move, and lower temperature, lower pressure when, again, the volume is not able to really adjust in any way. And then our Avogadro's law, where basically the volume is dependent on sort of the molecules or moles that are there. So as the volume increases, so does the moles of the gas. And as the volume decreases, so does the moles of the gas. And that's really to keep this situation here, the constant pressure. If we increase the volume, we need more gas molecules there to maintain the pressure. And if we decrease the volume, like over here, we would need less gas molecules, again, to sort of keep it at that constant pressure. So putting all these sort of gas laws together, your Boyle's, your Guy-Lussac's, your Charles' law, your Avogadro's law, we put them all together and we do get the granddaddy of them all there, which is the ideal gas law. So the ideal gas laws are PV equals nRT. And the ideal gas law is different than a lot of the other gas laws that we've seen up until this point. A lot of the other ones, pretty much all of the other ones that we've seen up until this point, is sort of a before and after situation. So we have two pressures, two volumes, two temperatures, two volumes, two pressures, two temperatures, two volumes, two moles. And for the ideal gas law, it's really just one set of conditions, and it's PV equals nRT. Also really important about the ideal gas law is that it is the most restrictive in terms of the units that you have to use. So whenever you use PV equals nRT, the units of these guys have to be certain units. So the pressure always has to be in atmospheres when you use the ideal gas law. So remember, if you have something like millimeters of mercury or torr, you need to divide by 760 to convert it to atmospheres. The volume, when you use the ideal gas law, it has to be in liters. N should hopefully be in moles unless something went really bad for you. T needs to be in Kelvin. And really the reason why everybody there needs to be in those specific units when we use the ideal gas law has to do really with R. R is the gas constant, and it is a number that you always have, is 0.08206. Some people in a lot of books now round to 0.0821. I personally use the top number most of the time because that's what they beat in my head and I can't get it out. But a lot of books now go to 0.0821. And the units, though, it has is liters times atmosphere divided by Kelvin times mole. And because this gas constant has all of those units, in order for everything to properly cancel out, the units of everybody else in the ideal gas law has to be those units: liters, atmosphere, Kelvin, and mole. The good news is, since you are always usually given R somewhere, or you can find R somewhere, you usually could just look at the units of R, and it should be a reminder to you that I need to make sure I do those conversions and get everybody in there. So we can use the ideal gas law, obviously, to solve for anything there, P, V, N, or T. And obviously R, which is the 0.08206, is not always just given to you in the problem. They assume that you have that value given to you, so a lot of times they won't give it to you in the problem, but you, again, always sort of have that. So a couple of other things and sort of how we get to that number that we see for R. Another important thing that you sometimes will come across is this idea of STP. And STP stands for standard temperature and pressure. And when they say something at STP, it actually does have values. The temperature is meaning that it is 273 Kelvin. the pressure is 1 atmosphere. So in a problem, it says calculate the volume at STP. If you need to go into the ideal gas law, for example, you would go in with a temperature of 273 Kelvin. You would go in with a pressure of 1 atmosphere. So when they do say STP, it does stand for something. Now, there is an important sort of relationship that can also help you not necessarily have to use the ideal gas law in certain problems. And it is only at STP. So only at STP, if you take 1 mole of any gas, it will have a volume of 22.414 liters. So this is a conversion that you could use. Again, we'll put little stars around it. Only at STP. So if the temperature is not 273 and the pressure is not 1 atmosphere, you cannot use that relationship. You have to use the ideal gas law. If it is at STP conditions, you could actually use that relationship without using the ideal gas law. But if it's at STP, you could still use the ideal gas law. You could just put the values in. So it is, if it is at STP, you can use that relationship or the ideal gas law to solve the problem. Or if it's not at STP, you can only use the ideal gas law. You cannot use that relationship. So that's really important. Again, that relationship, sometimes people want to use it everywhere in every calculation, but it is only specifically when you're at STP conditions. And that is actually how we do get the gas constant here. And if we solve the ideal gas law for R and put in everybody here at STP conditions, we end up with that 0.08206 number. And again, you can see this is why none of the units cancel. And we end up with all 4 of those units still in there. Any questions on that there? And again, if you do have questions, feel free to ask them. We'll go back and all that good stuff. And if you don't, why don't you give this one a try here? We want to calculate the pressure in atmospheres exerted by 1.82 moles of SF6 gas in a volume of 5.43 liters at 69.5 degrees Celsius. So take a minute or so here and see what you come up with. Okay, so again, if you sort of follow the same approach, you pull out the information. We're looking for a pressure. We have moles. We have a volume. And we have a temperature. So again, we pretty much have one of everything. You could kind of see PV equals nRT. Remember, you always have R, which is a constant. So we would want to use PV equals nRT. In this case, we have the volume, N, R, and T. We would want to solve for the pressure by dividing the volume to the other side. Now remember, we do want to be careful with this one, right? We want to make sure everybody's in the right units. So our moles are good, our liters are is what our volume needs to be. But again, here we do need to convert our temperature. So we'll take 69.5 plus 273. That's going to give you 342.5 Kelvin. So now we could put everything in. We got 1.82 moles. We have our 0.08206 liters atmosphere Kelvin mole. We have our temperature, which we converted to Kelvin. For some reason, don't want to write that in the last number there. And we're going to divide by our volume, which is 5.43 liters. In terms of units, kelvins will cancel, liters will cancel, our moles will cancel. That's going to leave us the only unit left, which is atmospheres, which is good. And 1.82 times our 0.08206 times 342.5 divided by our 543 gives us a pressure of 9.42 atmospheres in this particular case. Any questions on that calculation? Now, obviously, some variations of this calculations is instead of you're given moles, a lot of times you're given grams. So sometimes you have to convert it to moles, and that we do again like normal with the molar mass from the periodic table. So that's a common conversion you have to do. In addition to the temperature, obviously, that needs to go to Kelvin. Another common one is a lot of times the volumes in milliliters. So a lot of times we do have to take it to liters. So our 1,000 milliliters equals a liter is another common sort of conversion that you sometimes will have to use. So it won't always be sort of this straightforward in the sense of units. So a lot of times you have to do some other sort of conversions. But again, you want to make sure everybody's converted into the right units. Any questions on that there? Okay. So why don't you give this one a go? We want to know the volume occupied by 49.8 grams of HCl at STP. I'll give you some info, maybe. There we go. Hydrogen is 1.008 grams per mole from the periodic table. Chlorine is 3545. Okay. So take a minute or two here and see what you come up with. We're looking for a volume of that many grams of hydrogen chloride gas at STP. All right, so let's take a look. I see we got an answer down there, looking pretty good. So here we do have the grams of HCl, which is 49.8 grams. And from that, as we just talked about, we can get the moles. So we would want to use the molar mass from the periodic table. So we're basically just going to add those two guys together up on top. You get something like 3646 from the periodic table. And that would actually get us, obviously, 2 moles. And we'll call it 1.37 moles, give or take some rounding. So we have moles. We also have STP, which again does stand for a temperature 273 Kelvin. Also stands for a pressure of 1 atmosphere. We are looking for a volume. So again, here we have basically, if we think about PV equals nRT, we have the pressure, we have the moles, R is a constant, and we do have temperature. So one way you could solve this is you could solve it using the ideal gas law, which is V would equal nRT over P. And if we put our numbers in there, we will get 1.37 moles. We'll take our 0.08206. Here's atmosphere, Kelvin, and mole. Our temperature, which again would be 273 here at STP, all divided by our pressure, which would be 1 atmosphere at STP. Atmospheres would cancel, Kelvin would cancel, moles would cancel. Gonna leave us liters, which is good because that is a volume that we're looking for. And if we do it that way there, we end up with 30.7 liters with a little bit of rounding, right? Depending on where you round it. Now, this is one way you could do this problem, which obviously I can't remember any other way to do this problem. You can put it into the ideal gas law, as we were talking about earlier. Not a problem. You just put 273 in for the temperature. You put 1 atmosphere in for the pressure. But there is another way you could solve this problem, and that is because we are at STP. And if you remember, when we are at STP, and only when we're at STP, 1 mole of any gas will equal 22.414 liters. So what we could have done is, as soon as we got the moles of our gas, we could have just took the moles and used that relationship that 1 mole is 22.414 liters. Again, the moles would cancel out in this case. And if you chose to do it that way, you will essentially get the exact same answer of 30.7 liters. So because we were at STP, we did have these couple of options as to how you could solve it. You could see that perhaps the 22.414 might have been a little quicker of an option, but you could also see if you could not remember to do that, or if you weren't sure you should use that, you could always still go into the ideal gas law and you'll get the same answer. So again, as mentioned before, this relationship here is only at STP can you use it. So again, if it's not STP, do not use that relationship. But if it is at STP, you can. Any question on where any of the numbers came from, how we got anything here? And it looks like you did pretty good in there. Slight difference, just probably from rounding. Any questions on any of that? Okay. So we have not learned enough gas laws, so we should learn probably some more here. So there is one that relates really all 3 of the variables together, our pressure, volume, and temperature. And that gives us basically this gas law on the bottom. If we really solve the ideal gas law for R, and R is the same number, So R obviously is the same number. That means we could put both of these guys equal to each other, which we get down here. And in most cases with gases, if you don't open the lid, the number of moles should remain the same. So that brings us down to here, which is P1 V1 over T1 equals P2 V2 over T2. Just like every other gas law here, the temperature does need to be in Kelvin. In terms of the other units, the pressures on both of those, it doesn't matter what unit you choose as long as they are the same unit. So they need to be atmospheres on both sides. They need to be millimeters of mercury on both sides. Same thing with the volume. It really doesn't matter as long as the unit for the volume is the same on both sides. So either milliliters or liters on both sides. And this is the one I think that gives people the hardest time in terms of rearranging. So again, just it's easier for you to think about it this way, as you cross that equal sign, just move everybody into, again, the opposite locations if you need to rearrange and solve for it. So this is what, again, is sometimes referred to as the combined gas law. Because it pretty much combines everything together. The nice thing as well about this gas law is if you're not big on remembering Boyle's law, Charles' law, Guy-Lussac's law, you could actually use it to figure those out. Again, if you were doing Boyle's law, if you knew it's at constant temperature, you just take the temperature out of that equation and you got P1 V1 equals P2 V2. If you're doing Charles' law, which is constant pressure, you just take the two pressures out. You have V1 over T1 equals V2 over T2. You're doing Guy-Lussac's law is constant volume. Take the volumes out of each side, and you'll have P1 over T1 equals P2 over T2. So you could actually get a lot of the other gas laws from this particular one. You essentially just take out of it whatever's being held constant, and it will drop you into the gas law that you need. So let's take a look at our rearranging skills here. So give it a go. We're looking for the new volume of this gas. If we started at 27 degrees Celsius, 9.55 liters, 2.97 atmospheres, and the pressure goes to 8.25 and 125 degrees Celsius. So calculate the volume, see what you come up with, and we'll talk about it in just a second. All right, so let's take a look and see how we're doing. So again, if you're not sure, you can pull that information out. So where'd we go? There we go. Maybe. We have a temperature that is 27 degrees Celsius. We have a volume that is 9.55 liters. We got a pressure that is 2.97 atmospheres. We then change the pressure to 8.25. Our temperature goes to 125 degrees Celsius, and we are looking for a volume. So again, you should hopefully be able to recognize the combined gas law, which is the one we just saw there. P1V1 over T1 equals P2V2 over T2. In this particular case, we are looking for V2. So again, we're basically going to take our P2 and move it down. We're going to take our T2 and move it up. And if we do that, that will technically give us V2 equals our P1 V1 T2 divided by our T1 and P2. Now, in terms of units and everything, we do want to make sure we're good. We have atmospheres here and atmospheres here, so that's okay. And like usual, we do need to convert our temperatures. So again, we could call all these first values the ones, call the second values the twos. And if we do our conversion there, 125 plus 273 gets us to 398 Kelvin. I'll write that right, 98 Kelvin. And if we add 273 to our 27, gets us 300 Kelvin. So again, we want to make sure that we put everybody in the sort of the right spot. So our P1 is 2.97. Our V1 is 9.55 liters. Our T2 is 398 Kelvin. Divided by our T1, which is 300 Kelvin. And our P2, which is 8.25 atmospheres. Our atmospheres are going to cancel. Our Kelvin's going to cancel. That's going to leave us liters, which is good because that's what we're looking for at volume. And if we do all that good math there, we end up with 4.56 liters as our answer. Any question on that? And it does make sense if you sort of think about what's happening with our other sort of variables. Our temperature went up and our pressure went up. And this means that our volume actually went down. So that would make sense. Smaller volume with a higher temperature and would result in a higher pressure. Any questions on that? So again, I'd say this one gives people sort of the hardest time, the rearranging of it. And then again, very common people, again, put like T2 in the wrong spot or T1 in the wrong spot. So you do want to make sure you got everybody in the right spot. Any questions on that particular one there? Okay, so the next thing we're going to talk about in terms of gases is a couple of ways that you could calculate some properties of gases. The first way that you could calculate the property of a gas is to look at the density. And the density of a gas is the same as what density normally is, which is mass over volume. And you basically take the pressure times the M here. The M here is the molar mass in grams per mole. So that M is the molar mass in grams per mole. And R is our gas constant. T is our temperature. And these are really all, as I'll talk about in just a second, these are really all based off of the ideal gas law. So you do want to make sure, just like you would be using the ideal gas law, that all these units basically match the ideal gas law. So you do need to make sure that your pressure is in atmospheres. you need to make sure that your R's, obviously the gas constant we use, temperatures in Kelvin, in our grams per mole. And this will give us, if we just look at units, we would have atmospheres for the pressure. We would have grams per mole for the molar mass. We would have our liters, atmosphere, Kelvin, and mole for our gas constant. And we would have our Kelvin for our temperature. Kelvin would cancel, moles would cancel, atmospheres would cancel. So as we talked about at the beginning of this chapter, when we do the density of a gas, we usually will end up in units of grams per liter. So that's usually what you end up with in terms of the units. And again, you want to kind of basically treat it as a sort of like ideal gas law sort of situation. We could also calculate the molar mass, for example, of a gas by using this equation here, which is also really based off of the ideal gas law. Our densities in grams per liter, just like above. Our R's are gas constant, which is the same units, our liters, atmosphere, Kelvin, mole. Our temperatures in Kelvin, and our pressures in atmospheres. So unit-wise, atmospheres will cancel, Kelvin will cancel, liters will cancel, and you will be left with grams per mole, which will essentially be the units, obviously, of molar mass. So these are sort of two quick ways that you can, if you remember these formulas, get to sort of the answer. So if you can't remember it, so for example, let's say if we had let's see here, let's say we had let's say, for example, we had 12 grams of nitrogen gas at 27 degrees Celsius and 1.25 atmospheres. What is the density of N2 in grams per liter? So why don't you take a moment and try that one out, and then we'll go over it. 1401 grams per mole is the molar mass of nitrogen. So take a couple of minutes here and try to calculate the density of this guy. I will too, since I just made up the numbers, and we'll see if we end up with the same numbers here. Okay, so I'm going to show you how to solve it again a different way. Obviously, you have all the information you would need to just plug and chug into this top equation. But sometimes we might forget the top equation or any of these equations on this board. So both of these things, both the density and the molar mass, can both be achieved by really using the ideal gas law. And that's really what both of these are really based off of. And if we look at the ideal gas law, for example, which is our PV equals nRT, in this particular problem, we do have the pressure given to us, we do have R always, and we do have T. So we can actually rearrange the ideal gas law for N divided by V. And if we do that, that will give us P over RT. And if you think about the units here of N is moles. You think about the units of volume is liters. That is really the molarity of a gas, basically. So you could actually rearrange the ideal gas law and solve for N over V, which will give you basically moles per liter. Now, if you think about what we're looking for the density in grams per liter. And out of that, we actually do have the top part. That is the 12 grams that was given to us in the actual problem. So what we, I'm sorry, we're looking for, yeah, got ahead of myself there, sorry. We're looking for grams per liter. So we have all the information here to solve for our moles per liter, and we would put it in there 1.25 atmospheres. We would do our R, which is 0.08206 liters atmosphere Kelvin mole. And like usual, since this is the ideal gas law, we want to convert our temperature into Celsius. And that's 300 Kelvin. And if we look at what cancels out, again, atmospheres cancel, Kelvin cancels. When we divide that, the moles go to the top, the liters go to the bottom, and we end up with moles per liter. And if we do that, we have 1.25 divided by 0.08206 divided by 300 gives us something like, find my pen where it went, there it is. Gives us something like 0.0508 moles per liter. Okay, so what I was trying to do earlier is this is close to what we want, right? We're at moles per liter, but we do want to end up in grams per liter. So to do that, what we need to do that is really just going from grams to moles, right? Or moles to grams. And what that allows us to do is the molar mass of that guy there. So in this particular case, we would take the molar mass of it, and the molar mass of, and by the way, it's a bad question. You didn't need the 12 grams. That's what happens when you kind of make it up in your head. What we would use here is the molar mass of N2, which would be 2 times 14.01. Come back here. Thank you. 1401, which would give us 2802 grams per mole. The molar mass will basically cancel out the moles, and that will leave us 1.42 grams per liter. So this is really the same thing you would get if you went into this equation and I wrote a better question where I didn't give you extra information that you actually don't need for this problem. But you can see that hopefully basically those equations that we see on this screen is really based off of the ideal gas law. And you could always use sort of the ideal gas law to solve for either one of these things, density or molar mass, and just think of it as a conversion sort of problem at that point. Or again, you can memorize these formulas and plug and chug into them. Sorry about that. What happens, I guess, when you try to make up a problem on the fly there. Let's look at a problem that should work a little bit better since it has already been made up. And why don't you give this one a go? Why don't you calculate the molar mass of this gas? Again, a reminder, molar mass is grams per mole. And see what you come up with. Again, you shouldn't have extra information in this particular problem. Okay, so let's take a look at this problem, which obviously should work out better than the made up one I just did there. In this case, again, we're looking for molar mass. So we are looking for grams per mole. And you can, again, use that formula that we saw on the previous page and kind of plug in the numbers. Again, if you should not remember that formula, you could always default back to our ideal gas law, which is really where both of those come from. This is what I think I was thinking about in the last problem, but here we actually do have grams given to us, which is really the top number there, which means really in order to find the molar mass, the thing that we're missing is moles. And if we think about the other information that's given to us in this problem, we have a volume that's 2.1 liters. We have a pressure that's 1 atmosphere. And we have a temperature that's 27 degrees Celsius. which of course we do need to convert into Kelvin, which would be 300 Kelvin. So again, if we think about the ideal gas law on this particular problem, we have P, we have V, we always have R, and we do have T. So that we are missing N here, and that really is the other thing that we need to calculate the molar mass. So we would want to use the ideal gas law here again if you could not remember that other equation, and you could solve for N, and you could take 1 atmosphere, take the volume, which is in the correct units as well. Make sure you write it in there right. We're going to divide by our R. And our temperature, which obviously needs to be converted to Kelvin. Everybody's going to cancel except for moles in this case. And this would give us 1 times 2.1 divided by 0.8206 divided by 300 Kelvin gives us 0.0853 moles. And now we have both things that we need to figure out the molar mass. We have the grams that was given to us in the problem divided by the moles we just calculated from the gas information. And we would end up with something like 54.3, 54.5 units or grams per mole, as they don't cancel out in this particular case. So like I said before, you can use the two formulas that we saw on the previous page. Again, if you can't remember them, you should always just think about using the ideal gas law and think of it as sort of a conversion factor and getting things into the right units. Any questions on how to calculate the density or the molar mass of a gas? Obviously, in my really bad example last time, you would not have needed the grams. I think I got this molar mass in my head when I was writing it. Any questions on any of that? Okay. So let's talk a little bit about gas stoichiometry here. And gas stoichiometry is pretty much like regular stoichiometry. The only difference is somewhere along the way, you essentially will use the ideal gas law. So a lot of times at the end of the problem, you'll use the ideal gas law. Sometimes maybe at the beginning of the problem, you may use the ideal gas law. If you do use the ideal gas law at the beginning of the problem, you most likely will be solving for moles. If you use the ideal gas law at the end of the problem, a lot of times you will be solving for volume. So a lot of times when we do some type of reaction involves a gas being generated, we're usually interested in the volume of the gas that's produced. So again, a lot of times, you know, at the end of the problem, you'll use your PV equals nRT, and you'll oftentimes solve for V. If you happen to have used it at the beginning, most likely you would be solving for N. And really the middle part of stoichiometry problem is really the same. You really want to follow the same sort of 4 steps, especially if it's a basic stoichiometry problem. You would want to make sure you always have a balanced equation. You want to convert to moles. So if you have grams or something like that, you would use the molar mass. If you use the ideal gas law at the beginning, you would solve for N, which would get you moles. You then would do the mole to mole relationship between the two things. And finally, at the end, you would convert those moles into some other unit. And like I said, a lot of times in these problems at the end, you're going to use the ideal gas law and solve for something like volume and figure out how much volume of a gas that you actually produced. All right, so I think maybe this is a good stopping place for today. So we will stop here today in terms of the lecture. We're nearing the end of this chapter, which will be the last chapter that will be on our exam. A reminder that our exam has been moved to 1 week from Thursday, and it will cover through this chapter. So we should finish up this chapter on Thursday. Hopefully we'll maybe get into some chapter 9 as well on Thursday, which the notes are up there, up online as well. So exam will be 1 week from Thursday. whatever date that is, May something. It is, it looks like it's May 14th. Like I think I sent the announcement out. Again, it will cover through chapter 8, which is what we will finish on Thursday. For today's lab and this week's lab, we are starting the titration experiment. Like we're physically doing it. We're starting the titration experiment. And it will be the lab that we'll do all week. It will be posted as soon as I'm done here up online. You have 3 different videos to watch, one for each part of the experiment. So part 1, part 2, and part 3. Part 1, you'd be standardizing your sodium hydroxide, figuring out the molarity of your sodium hydroxide in that titration. And part 2, I believe you'll be doing a titration of an unknown acetic acid and trying to figure out the percentage of acetic acid, I think, in vinegar, if I'm not mistaken. And in part 3, I think you'd be figuring out the molar mass of an unknown acid in that titration. So we already talked about titrations, solution stoichiometry. So you should hopefully be okay, I hope, on some of that. Some of the calculations are slightly difficult. If you do have some questions, I will remind you that you do need some balanced equations when you do it. And you want to make sure you have the right balanced equations for each of the parts so that you get the right mole-to-mole relationship when you're doing that solution stoichiometry. It is going to be a formal lab, so it was actually the biggest experiment we usually do. So it is going to be a formal lab, which means you do need to type up a lab report for this one, and make sure you get it in by its due date, which I think is next week, at the end of next week, I think, sometime, if I'm not mistaken. So I will be obviously here for lab. We'll start around this normal time, maybe 7:15, 7:20. If you do have some questions on that, you could obviously come in and ask your questions. But I will get started doing it. You do have to write down, obviously, the stuff in your carbon pages, the information, because he's going to give you some information in the video that you need to write down to obviously be able to do the calculations. And you will have to type up a lab report like the hydrate lab and the chemical formula type lab. So it will be a lab report like that for this particular one. And again, this week during lab, I'll be available obviously to answer any questions that you may have in terms of the calculations or anything like that in terms of that. Any questions on anything? Okay, so the lab and all that should be up in a couple of minutes. And again, I'm going to start probably the lab lecture around 7:15-ish or so. And again, if you have questions, feel free to come by today, on Thursday. You can always email me as well. But again, I would recommend not waiting to the last minute to do all the calculations and all that kind of stuff. Make sure you work on it all this week, and then you should be in good shape for next week. Remembering you do have an exam next week, so don't wait till next week to do the experiment and the exam. All right, have a good night. I'll see you later in lab. If you have questions, again, they will be up there very shortly. It's not up there right now, in a couple of minutes. And I'm going to stop this one for now, I think. The exam has been moved. And I think I sent out an announcement the other day on, I think last week on Friday, I sent out an announcement and mentioned it. The exam is a week from Thursday. So it should be the 14th, if I'm not mistaken, on the date.